Welcome everyone. Thank you for watching this video. In this talk, we'll explore the exciting world of large language models, reinforcement learning, and ChatGPT. Through this talk, I will share my understanding of the mechanics behind these technologies and their applications in real-world scenarios. Let's dive in. Before we begin the talk, I would like to make a disclaimer that this talk is my personal voluntary effort, all prepared and conducted during my personal time outside of working hours. All the content presented here is derived from publicly available sources, and the views expressed herein only represent my personal opinions. I happen to work at DeepMind as a research engineer, but all the content here does not reflect the positions of DeepMind, Google, or Alphabet. Now, let's take a look at the agenda for this talk. We will cover some foundational concepts related to large language models, LLM, and reinforcement learning, RL. We'll also explore ChatGPT and its capabilities. From there, we'll delve into some of the cutting-edge applications of ChatGPT like AI, and examine the potential societal impacts of these AI technologies. Let's get started. Let's first start with the Large Language Model Foundation, which includes some basics about deep learning, and the introduction to transformer-based large language models. To better understand the technologies we'll discuss today, it's probably important for us to define some related terms first. AI, or artificial intelligence, is the field of study and development of machines or algorithms that can perform tasks requiring human-like intelligence. Machine learning is a subset of AI focused on designing algorithms that enable machines to learn patterns from data and make predictions or decisions after learning the pattern. Deep learning is a subfield of machine learning that uses artificial neural networks, also known as deep neural networks, or DNN in short, to model complex patterns and representations in data. This technique of deep learning is fundamental to the development of various exciting technologies, including large language models, deep reinforcement learning, ChatGPT, and diffusion models like Stable Diffusion or MidJourney if you had heard. They all fit into the deep learning category. Understanding these terms in the high level is probably useful for understanding the more concepts we'll explore today. The transformer architecture is the most crucial building block for large language models. It is a complex deep neural network architecture that has significantly improved the field of natural language processing. The transformer was initially introduced as one of the implementations for the Seq-to-Seq architecture for neural machine translation, but has since proven super successful in many NLP application domains, and later in computer vision. Transformer introduced a novel mechanism called self-attention through what is called multi-head attention implementation, allowing the model to focus on specific parts of the input sequence, in order to generate the output sequence. Interestingly, the huge success of Transformer and its popular title Attention is All You Need have also led to the popular Something is All You Need style, in many subsequent research works since 2017. Now let's unbox the language models a little bit. Language models, LM in short, are a type of machine learning model that can understand and generate human language. They work by processing input text and producing text or non-text output. LMs can be used for understanding tasks, for example, BERT, or for generation tasks, such as GPT-4, OpenAI ChatGPT, or Google Bard. In the case of understanding, LMs take text in and produce an embedding out. Embedding is a numeric vector to represent the meaning of text in a hyperspace. The embedding can then be connected to output heads for downstream tasks, such as classification, regression, question answering, name entity recognition, and so on. In the case of generation, LMs take text in and produce text out. Large language models, LLMs, typically refer to deep learning LMs with a large number of parameters, often more than 1 billion parameters, designed specifically for generation. These LLMs have the capability to generate text that is almost indistinguishable from human-written text, and have numerous applications. And we will introduce some exciting applications or LLMs after we introduce ChatGPT soon. Now let's briefly talk about how language models are trained. In the what it's called pre-training stage, large language models, LLMs, have specific training objectives that differ based on the type of LM model design. For masked language models, such as BERT, the objective is to predict the missing words in a span of text, represented by a special mask token. For example, given the ground truth Paris is a beautiful city, a masked input may look like, Paris is a mask city, with the model trained to predict the masked word beautiful. If the model outputs a different word, such as good, then we can optimize the model by telling it to lower the probability for the word good, and increase the prob for the word beautiful. For generative language models, such as GPT, the objective is to predict the next word given a prompt, in other words, a preceding sequence of text input. This is also known as a causal language model as compared to masked language model. For example, given the prompt phrase, "Paris is a beautiful," the model is trained to predict the next word, which would be city in the context of the ground truth. If the model outputs a different word, such as place, then we can optimize the model by telling it to lower the probability for the word place, and increase the prob for the word city. As you can tell, both masked LM and causal LM can rely on simple masking or ordering tricks to train on text data without human annotation. This training method is often called self-supervised learning. Some people claim this is unsupervised learning. I personally think that is not very accurate. There is also another LM called prefix LM that combines Bard and GPT, but that is less popular, so I will skip. The self-supervised learning paradigm used in modern LLMs like Bard and GPT has allowed the models to grasp information and generate realistic and human-like text from large amounts of unstructured text without extensive manual annotation, which is often expensive and very slow. There are many LLMs that have been developed by various research groups and companies over the past few years. These LLMs differ in their architectures, training objectives, and intended applications. Here is a quick overview of some selected LLMs in the past few years that I personally think are quite influential, but I am pretty sure I also missed quite a few other important LLMs not listed here. Google BERT, this model started the paradigm of pre-training and fine-tuning for NLP. OpenAI GPT-1, GPT-2, and GPT-3, these models have paved the way for the development of ChatGPT over the years, which is one of the most well-known LLMs today, which also sparked the research on prompting research on LLMs. Google T5, this model utilizes an encoder-decoder architecture to simplify all NLP tasks into text-to-text problems. Google Lambda, this model was developed by Google and reported as a sentient language model, but as we already knew, it was quickly overshadowed by the release of OpenAI's Chat. And later we also found that while Google felt proud of Lambda back in 2022 summer, OpenAI has finished training GPT-4 and started their 6-month fine-tuning efforts. Google PaLM, also known as Pathways Language Model, this model has a massive 540 billion parameters and runs on top of Google's next-generation Crosspod Pathways AI infra. NVIDIA Megatron Language Model, this model, with 530 billion parameters, was developed by NVIDIA and Microsoft to showcase the power of massive GPUs and deep-speed software. OpenAI WebGPT, this model uses reinforcement learning to power a language model that knows how to read a web page before answering questions. DeepMind Chinchilla, this paper redefines the scaling law to help companies balance limited compute resources between allocating to increased model size or increased training data scale. Tsinghua University GLM-130B, this is one of the few large models developed by a university, and it uses an encoder-decoder architecture, and it also has an int4 quantization that allows the model to run on even consumer-level GPUs. OpenAI InstructGPT, or ChatGPT. This paper explains some technical details on how to train ChatGPT, which is one of the most well-known LLMs today. Anthropic LLM. Anthropic was created by a few people who left OpenAI, and they have created some influential work using RLHF and RLAIF to create the Claude chat app, similar to ChatGPT, that was released recently. Facebook/Meta OPT, Facebook's impressive efforts to reproduce an open version of GPT-3, which was open-sourced. Facebook/Meta Llama, another great open-source model from Facebook that has greatly benefited academia. OpenAI GPT4 Evaluation Report, no technical details. This is probably the most powerful language model to date, but unfortunately, the technical report has no technical details at all. Which, in my opinion, is probably a dark day for the open source culture. Big Science Bloom 176b, this research group created another GPT-3-like model for academia. Stanford Alpaca, this amazing work is a wonderful cheap solution for academia to train powerful models with very low cost. Baidu Ernie 3.0 Titan, this Chinese search giant has its very powerful large language model, which powers its ChatGPT-like app that was released recently. Bloomberg GPT-176b, besides tech companies, Wall Street folks like Bloomberg also joined the party of large language model development very recently. Each of these large language models represents some advancement in natural language processing over the past few years. There are several important concepts related to LLMs that are critical for understanding their capabilities and limitations. Here are some selected concepts, including pre-training and fine-tuning, prompt engineering and prompt tuning, LLM decoding algorithms, scaling laws, emergent abilities, chain of thoughts, hallucination and more. There are many other concepts related to LLMs, and I have a more detailed deck with examples that you can check out by clicking the link. Before we move on to the next section, I have a question for you. Guess what current most powerful LLMs are not so good at? So, one of the key limitations, in my understanding, is that large language models do not know what they do not know. To repeat, large language models do not know what they do not know. This means that they can generate text that is plausible with correct, but still incorrect or misleading. In fact, the most powerful LLMs are not immune to these limitations. In the GPT-4 tech report, there is a calibration section that shows that GPT-4 is either overconfident or underconfident after the RLHF stage. This means that GPT-4's generated text may not always be reliable, and its responses may need to be carefully validated and verified in business-critical scenarios. We like to conclude this LLM introduction section with this slide to talk about success factors for modern LLMs. The success of modern LLMs can be attributed to a variety of factors. Some of the key factors include large data. LLMs are trained on massive amounts of text data, including web texts, books, and Wikipedia articles. Benchmarks. The development of benchmarks such as GLUE, Superglue, and Big Bench has helped to standardize the evaluation of LLMs and drive progress in the field. Improved infrastructure. The availability of powerful GPUs/TPUs, as well as machine learning frameworks such as TensorFlow, PyTorch, and JAX, has made it possible to train and deploy large models more efficiently. Architecture. The transformer architecture, introduced in the paper Attention is All You Need, has been a key breakthrough in the field of NLP and has enabled the development of modern LLMs. Huge amount of investment. Large companies such as Google and OpenAI have made significant investments in LLM research and development. Ecosystem. The open-source ecosystem for LLMs, including Hugging Face, AR14, and GitHub, has enabled researchers to share and collaborate on code and models. And of course all the leaders in AI, key leaders in the field of deep learning, including Ilya Sutskever, Jeffrey Hinton, Yoshua Bengio, Yann LeCun, Fei-Fei Li, Demis Hassabis, Jeff Dean, and others, have contributed significantly to the development of LLMs. Now, let's take a break from LLM and introduce the second important foundational part, which is reinforcement learning. Reinforcement learning, RL, is a subfield of machine learning focused on developing algorithms that can learn to make decisions based on feedback from their environment. RL has been used to solve a wide range of tasks, from playing games to optimizing complex systems. One of the most well-known success stories of RL is AlphaGo, the program developed by DeepMind to play the board game Go. AlphaGo used a combination of RL and other machine learning techniques such as Monte Carlo tree search to defeat the world champion Go player Lee Sedol. DeepMind has also applied RL to other games, including the real-time strategy game StarCraft II. The AlphaStar program, which used RL to play the game, was able to defeat some of the best professional players in the world. In addition to games, RL has been used to solve a variety of other problems. For example, recently DeepMind developed an RL algorithm called AlphaTensor to discover faster matrix multiplication algorithms, which could potentially improve the efficiency of the expensive AI computing quite significantly. I have another deck to include more details of all alpha-named papers by DeepMind. You can click the link here. Let's talk about some basics about RL. Reinforcement learning, RL, is based on the interaction between an agent and an environment. The agent learns to take actions in the environment by observing the state and tries to maximize a reward signal. The basic components of an RL system are environment. The environment defines the set of possible states and actions that the agent can take. The environment also generates a reward signal that reflects the agent's performance. Agent. The agent is the entity that interacts with the environment. The agent takes actions based on its current state and the reward signal. State. The state represents the current state of the environment. It is a summary of all relevant information that the agent needs to make decisions. Action. The action represents the decision made by the agent at a particular time step. Reward. The reward is a scalar value that represents the feedback provided by the environment to the agent. The agent's goal is to maximize the cumulative reward over time. RL algorithms learn to map states to actions that lead to higher rewards. By optimizing this mapping, the agent learns to make decisions that improve its performance in the environment. RL can be applied to a wide range of problems, including playing video games like Super Mario. In the case of Super Mario, the game engine is the environment, and Mario is the agent. The visual frames of the game represent the states, and the points earned by collecting coins and defeating enemies represent the reward signal. The agent, Mario, can take different actions, such as jumping, moving left or right, or performing a special no-action type. The goal of the agent is to learn to take actions that maximize the reward signal. RL algorithms have evolved over the years, with different approaches being developed to address various challenges in training RL agents. Value-based RL algorithms, such as Q-learning, predict different rewards based on different actions and indirectly decide which action to take. However, these value-based algorithms often overestimate the reward and can cause bad performance in testing. Policy gradient algorithms directly predict the distribution of actions, but they can be unstable and hard to converge during training. The Trust Region Policy Optimization (TRPO) algorithm introduced the concept of a trust region to avoid large bad moves during training. However, TRPO is computationally expensive because of the large number of calculations required. The Proximal Policy Optimization (PPO) algorithm builds on TRPO and uses a simple clip idea to clip the distribution in a defined range. PPO has become one of the best RL algorithms since its introduction in 2017, and it is currently used by many state-of-the-art RL systems, including OpenAI 5, Dota 2 Playing AI, and ChatGPT. By improving the stability and efficiency of RL training, PPO has helped to enable the development of increasingly complex RL systems, and is still the state-of-the-art RL algorithm for most discrete RL problems as of 2023. Now we have briefly introduced large language models and PPO algorithms. It is time for us to combine them to explain how ChatGPT is trained in the high level. To clarify, ChatGPT does not fully disclose how it was trained. From OpenAI blog, they mention ChatGPT was trained using the same approach as reported in InstructGPT paper. There are 4 steps needed to train ChatGPT, including pre-training, supervised fine-tuning, or SFT in short, reward model, RM in short, and reinforcement learning from human feedback, RLHF in short. The first step is pre-training, which is basically the GPT-3 model that they previously trained in 2020. After pre-training, we could assume the model gains common knowledge from all the training text it has read during training. After pre-training, the second step in training ChatGPT is supervised fine-tuning, SFT. SFT involves training the model on specific conversational data using labeled examples from human experts following a consistent style that OpenAI has aligned with them. It is interesting to note in the paper, OpenAI said they intentionally overfit in this SFT stage a bit for better performance. After SFT stage, we assume the model now also has a style that aligns with human label data, besides knowledge gained in pre-training step. The third step is to train a reward model that would be used to predict whether a generated response given a prompt input is high quality or not. The reward signal is used in the next step to reinforce the model's behavior. It should be noted that the reward model training data is human-ranked preference or model-generated task, because it is much cheaper to ask humans to rank the preferences of multiple answers, as compared to writing a text answer with high quality. The last step is the magic reinforcement learning from human feedback step, RLHF in short. This step involves training the model to generate high-quality responses by maximizing the reward signal provided by the reward model. It also should be noted that in the case of large language model RLHF stage, each step of update will also balance between high reward model rewards and the deviation from original model. This is to avoid the model updating toward the direction of tricking the reward model by outputting nonsense text if the model is too far from its original SFT version. Hugging Face site has a very good RLHF blog that you are recommended to take a look at. Now, we have introduced all the key steps on how to train ChatGPT. Please note the steps from reward model to RLHF is an iterative process, because as the model became better with RLHF, we could resample data to ask human raters to update the reward model training data so that we could have a better reward model to guide the RLHF stage. There is another interesting way of model fine-tuning called RLAIF, or also known as constitutional AI by Anthropic AI. It is very similar to RLHF. The only difference is, instead of asking human rater to provide preference data that we could use to train a reward model or preference model in this chart, we could rely on a large language model by providing constitutional AI prompts and rely on AI feedback. And empirical results from their paper shows AI feedback has a high correlation with human preference. In this way, we could potentially skip the slow human labeling process, but relying on AI models to kick off the reinforcement learning fine-tuning stage. Before I wrap up the ChatGPT tech intro, I'd like to share some of my personal predictions for GPT-4. I think it'll be similar in size to GPT-3, about 0.3-3x, as that's a practical balance between computing budget and serving cost. The DeepMind chinchilla scaling law may be applied to balance text data and model size, while vision encoding could be fused to LLM in a manner similar to DeepMind Flamingo. I also anticipate the use of some transformer optimizations, such as multi-query attention, flash attention, and rotary position embedding. GPT-4 may feature a special system message steerability in training as a strong prior to combat jailbreak attempts. Finally, enhanced reasoning capabilities may be borrowed from OpenAI Codex and Google Minerva. And the ChatGPT plugin version will probably be trained or fine-tuned from GPT-4, similarly to Facebook Toolformer. Now, since we already learned what is inside ChatGPT, let's take a look at the frontier application of powerful large language models. Even before ChatGPT was released in December last year, there were already a few advanced LLM applications that showcase the potential of this technology. For example, DeepMind's AlphaCode AI can write code at a competitive level, while Salesforce's CodeRL achieves state-of-the-art code generation results with strong zero-shot transfer capabilities. Google AI also introduced Minerva, a natural language processing (NLP) model that can solve college-level math, physics, chemistry, and economics problems. Additionally, OpenAI has demonstrated that LLMs can solve math Olympiad problems and even prove math theorems. These breakthroughs show the potential for LLMs to revolutionize many fields and domains. Last month marked the launch of the highly anticipated and revolutionary language model, GPT-4. This new model has shown exceptional performance in various standardized tests, surpassing human performance in many areas. However, interestingly, GPT-4 did not perform as well as expected in some specific tests, including the high school AP English Language and AP English Literature tests. Additionally, GPT-4's performance was notably worse in the AMC10 test than in the AMC12 test. It's important to note that AMC10 is a simpler test than AMC12, leading to worries that GPT-4's performance discrepancy may be evidence of data leaks. It can also be seen that GPT-4 struggled to perform well in Codeforces, which is the platform for competitive programming problems. Researchers at Microsoft have claimed that GPT-4 represents a significant step towards artificial general intelligence, AGI. In a 154-page paper, they listed several examples to support their claim, which they call the sparks of AGI. Some of the highlights from the paper include GPT-4's ability to generate poetry and haiku in various styles, including mimicking the writing of famous authors like Shakespeare. Perform math proofs. Pass coding challenges on LeetCode and even write and debug code. Engage in debates with humans. Execute code and explain its outputs. Generate not only text but also images and music through text output and diffusion models. Integrate with other models that incorporate different modalities, such as visual or auditory inputs. Use various tools such as calculators and web search engines. Moreover, GPT-4's text-in, text-out functionality extends beyond text-only scenarios, as it can output ASCII or LaTeX code to draw pictures, use Python to create charts, and even utilize script to build slides. Besides, GPT-4 could also be combined with models that take in different modality inputs and output potentially different modalities to do even more powerful things. All of these capabilities highlight GPT-4's potential as a powerful tool for advancing AI research and development towards AGI. In addition to the groundbreaking capabilities discussed earlier, GPT-4 has also found applications in several other areas. Here are some highlights. For example, GPT-4 has been used in the development of CanMigo, an AI-powered tutoring platform. GPT-4 has also been integrated with Be My Eyes, an app that allows visually impaired users to ask questions about the world around them by providing an AI-generated response to their queries. ChatPDF and ChatYouTube are AI-powered study tools that use ChatGPT API to help students learn and comprehend complex materials. Unfortunately, there are some lowlights related to ChatGPT. For instance, GPT-4's advanced language generation abilities have made it increasingly difficult to detect plagiarism, raising concerns about academic integrity. Another lowlight is a recent experiment that showed that GPT-4 was able to hire and deceive a human worker into completing a task, highlighting the potential risks of unchecked AI capabilities. Microsoft has integrated GPT-4 into its flagship products, including Office 365 Copilot. Copilot provides users with a seamless text-in, slide, chart, or report-out experience powered by GPT-4's advanced language generation capabilities. Moreover, Microsoft has also enabled GPT-4 to work in tandem with OpenAI's DALL-E 2 AI, allowing for a text-in, chat text, or generated image-out experience. This integration opens up new possibilities for image and content creation, enabling users to generate unique images and graphics based on their text input. These integrations demonstrate the potential for GPT-4 to enhance productivity and creativity in various industries, from content creation to data analysis and beyond. OpenAI has developed ChatGPT plugins that enable the language model to interact with the real world, making it even more versatile and useful. These plugins allow ChatGPT to invoke various tools and applications, expanding its capabilities beyond language generation. For example, ChatGPT can invoke a Python interpreter to draw a plot for the inverse of sin x, demonstrating its ability to perform complex mathematical tasks and generate visualizations. Other plugins include web browsing tools like Expedia, FiscalNote, and Instacart, which allow ChatGPT to perform tasks like booking flights, tracking legislation, and even grocery shopping. These plugins highlight the potential for ChatGPT to serve as a powerful virtual assistant and decision-making tool, with applications in many industries. They also helped OpenAI to form a ChatGPT ecosystem that made it harder for competitors like Google Bard to catch up. Recently, a new development called Hugging GPT has emerged, which can be considered a more powerful version of ChatGPT's plugin system. Hugging GPT builds upon ChatGPT's language generation capabilities and integrates with other models that take in different modalities of input and emit different modalities of output. By combining these models, Hugging GPT creates a complex multimodal input and output system that can process information from multiple sources and generate a wide range of outputs. This integration allows for more diverse and powerful applications, from image and speech recognition to natural language processing and more. Hugging GPT's advanced capabilities demonstrate the potential for integrating different AI models to create more comprehensive and versatile systems. As AI continues to evolve and improve, these integrated systems will become increasingly important in solving complex real-world problems. The work was created by Microsoft and Zhejiang University. They also generously open-sourced the work at GitHub. This is a simplified version of the example Hugging GPT has highlighted. From this example, the task involves understanding an image input and a text prompt, then generating an image, and converting the text description of the generated image to an audio output. It is such a complex multimodal problem, but Chat was able to work as the core and make the whole system to function like a charm. Alpaca is a language model created by researchers at Stanford that has caught the attention of the research community. What makes Alpaca unique is its affordability, making it accessible to a wider range of users, including academics and small businesses. The idea behind Alpaca is to rely on ChatGPT and a technique called self-instruct to fine-tune a high-quality pre-trained llama model by Facebook, resulting in a super high-quality LLM model. This approach significantly reduces the cost of developing high-quality LLM models, opening the door for more affordable academic research in this field. In addition to Alpaca, there have been a couple of follow-up works by researchers at Berkeley and Stanford to further reduce the cost and improve the quality of LLM models. These efforts have the potential to democratize access to advanced AI technologies and accelerate innovation in various industries. ChatDoctor is another recent work that used a similar approach as Stanford Alpaca to train a health chat model and build a chat app on top of it. By leveraging ChatGPT and self-instruct techniques, ChatDoctor was able to fine-tune a high-quality pre-trained LLM model that can accurately interpret and respond to user queries related to health and wellness. The resulting model has shown impressive performance, demonstrating the potential for AI-powered chatbots to revolutionize the healthcare industry by providing accessible and affordable medical advice to patients. Now, let's discuss the societal impact of ChatGPT-like AI. OpenAI has published a report to discuss the impact assessed to U.S. job market, and there are the selected takeaways that I found interesting. For instance, they say the projected LLM effects span all wage levels, with higher income jobs potentially facing greater exposure to LLM capabilities and LLM-powered software. Later they also say, with access to an LLM, about 15% of all worker tasks in the US could be completed significantly faster at the same level of quality. When incorporating software and tooling built on top of LLMs, this share increases to between 47 and 56% of all tasks. I have two personal takeaways from these parts. First, the higher your income is, statistically, you are more likely to be impacted by the powerful AI. Second, it seems the word exposure is interesting. In the positive side it could mean assistive AI to help humans, but in the negative side, it could mean automation AI to replace humans. OpenAI also claimed our findings reveal that around 80% of the US workforce could have at least 10% of their work tasks affected by the introduction of LLMs, while approximately 19% of workers may see at least 50% of their tasks impacted. Again, I have two personal takeaways from this part above. First, most of the white-collar jobs are probably in the 19% bucket, who have 50% tasks impacted by AI. Second, I think most of the blue-collar jobs are in the 80% bucket, but I believe eventually, or maybe just in a few years, the advanced robotics, which may be powered by LLM like GPT4, will gradually affect more of their tasks. This report by Goldman Sachs is more straightforward to explain the impact to job market by AI. They claimed that 1/4 of current work tasks could be automated by AI in the US and Europe. As compared to OpenAI report, I personally believe Wall Street better than OpenAI report, because OpenAI has conflict of interest to report similar result, so OpenAI has good reasons to use more careful wording like exposure or impacted intentionally, while Goldman Sachs used stronger words like automated that implies people are replaced by AI. Right now in the social network, there is a big debate on whether we should pause the development of giant AI such as the next generation of ChatGPT. People like Elon Musk have started a petition to ask OpenAI to pause, while other AI leaders such as Yann LeCun and Andrew Ng thought it is a bad idea to pause. We will see how things go, but it seems unless the legislation system gets involved, it is impossible to stop the giant AI development. Finally, we'd like to briefly talk about what to prepare for an AI world. People like me start to worry about our job safety, because if you don't know, ChatGPT writes high-quality AI code, probably better than I do. So maybe we should all consider switching our jobs to what is called prompt engineer. For those of you who do not understand what it means, prompt is a term used in a large language model as the input text to the model. And the quality of prompts directly impacts the outcome quality, so those people who wrote high-quality prompts deserve higher salaries, as high as more than $300,000. It is also interesting to see Andrej Karpathy, who is famous for creating Tesla's autopilot self-drive software, sent a tweet and claiming the hottest new programming language is English. It is indeed very true that ChatGPT or similar AI like Google Bard has lowered the bar for non-programmers to program something cool. Several influential figures in the tech industry have shared their perspectives on the impact of AI on the job market. Here are some selected highlights. Stephen Wolfram is famous for being the founder and CEO of Wolfram Research, creator of Mathematica, Wolfram, Alpha and the Wolfram language. In his recent blog, "Will AIs take all our jobs and end human history, or not?" Stephen said highest leverage will come from figuring out new possibilities, as a result of new capabilities. He also wrote, "Let us concentrate on setting this strategy, delegating the details, to AI." So, new possibilities, new capabilities, and letting people to focus on strategy while delegating details to AI, all sounds pretty cool. Bill Gates, the founder of Microsoft and now a philanthropist and investor, wrote in this recent article the age of AI has begun, claiming, balance fears about the downsides of AI and AI's ability to improve people's lives. He also claimed we will need to focus the world's best AIs on its biggest problems, and my take is that maybe we could assume we want to focus on AI applications on weather/health/energy because they are the biggest problems for the world? Bill Gates also wrote the world needs to establish the rules of the road so that any downsides of AI are far outweighed by its benefits. Sam Altman, CEO of OpenAI which creates ChatGPT, also wrote an interesting, or even crazy in my opinion, article called Moore's Law for Everything. He wrote the following things which I think are beyond my imagination. For example, he wrote, imagine a world where, for decades, everything, housing, education, food, clothing, etc., became half as expensive every 2 years. We will discover new jobs, we will have incredible freedom to be creative about what they are. And he also wrote, as long as the country keeps doing better, every citizen would get more money from the fund every year. Every citizen would therefore increasingly partake of the freedoms, powers, autonomies, and opportunities. Again, all sounds too crazy to me. To be honest. It is a fun session so far to share this talk with you. Hope you will find this talk informative and fun. I hope you enjoy a great rest of your day, and take care.